5, 4, 3, 2, 1. Ignition. Liftoff. Go SpaceX. Go SpaceSat G1.
Right now, more than 8,000 satellites silently orbit the Earth. Most of them were built on American soil, inside factories so advanced that a single mistake of a few milliseconds could cost millions. But few people know how these massive machines actually come to life. Up there, every American satellite plays a vital role. Some track hurricanes, others guard borders, and many keep the global communication systems running that connect our entire planet. None of this happens by chance. Behind each satellite lies a complex design, studied for months before the very first piece is ever built. Inside the factories, everything starts with the satellite's main body, made from ultralight and incredibly strong metal alloys. Each structure is engineered to withstand extreme heat and the violent forces of launch. Engineers inspect every weld and every joint, because even the tiniest flaw could mean the total loss of a mission worth millions of dollars.
Go SpaceX. Go SpaceSat G1.
Then comes the brain of the system. Sensors, antennas, solar panels, and circuits coated with precious metals like gold and titanium. These parts are assembled in clean, climate-controlled rooms, completely free from dust and humidity. The goal is simple. When the satellite is more than 20,000 miles above Earth, it must still perform with the same precision it had the day it left the factory. The result is stunning. A machine that weighs less than an average car can manage global transmissions, predict disasters, and even help guide airplanes. All of that happens from a place that feels untouchable, yet depends entirely on these hidden American factories. It all begins at the launch site, a high-security area where every second is carefully timed. The fully assembled satellite is sealed inside a protective capsule that keeps it safe until it reaches orbit. Then it is attached to the main rocket, a towering metal giant packed with hundreds of tons of liquid fuel, ready to create the force needed to escape Earth's gravity. When the countdown ends, the pressure is beyond imagination. The engines ignite, releasing flames hot enough to melt steel. In seconds, the rocket cuts through the sky, piercing clouds and reaching speeds of over 17,000 miles per hour. Inside, the satellite must endure vibration, G-forces, and searing heat, a true test of technological endurance. During ascent, the rocket separates in stages. Each section has a specific task and detaches at the exact right moment, reducing weight and maintaining thrust. Finally, when the last stage breaks away, the satellite is released into its designated orbit with millimetric precision. Small internal engines make final adjustments, locking it into position around the planet. In less than an hour, what began as a metallic structure inside an American factory becomes a fully operational piece of space technology. And from that moment on, its mission begins: to observe, to measure, to connect, and to protect. Building a satellite requires absolute precision. It starts in the digital design room, where engineers define every measurement, including size, weight, and purpose. Each detail depends on the mission. A weather satellite, for instance, needs highly sensitive sensors, while communication satellites demand long-range antennas and wide solar panels. Nothing is built at random. In American factories, aluminum forms the backbone of most structures. It is cut, molded, and reinforced with carbon fiber layers, creating a shell that is light but strong enough to survive the launch and the extreme temperature swings of outer space. Every component goes through strict inspections, including vibration tests, heat simulations, and even artificial radiation exposure. The electrical system is the heart of the satellite. Wires, circuits, and microprocessors are assembled by hand using microscopic tools. Even the smallest deviation could compromise the entire mission. To maximize energy efficiency, solar panels are made with ultra-pure silicon cells that convert sunlight into electricity with minimal loss. Before launch, the satellite faces its final trials inside vacuum chambers, exposed to temperatures ranging from -300 to over 300 degrees Fahrenheit. If it passes every test, it is cleared for space. And that is when months of work transform into a mission that could last for years, orbiting high above, silently shaping the modern world. Across the United States, some of the largest space factories on the planet operate far from the public eye. These are enormous facilities surrounded by security and silence, where thousands of engineers work in continuous shifts. Each section is dedicated to a specific stage of production: structural assembly, electrical system integration, vibration testing, and final calibration. Everything takes place in controlled environments, with temperature and humidity monitored every single minute. These factories look more like high-precision laboratories. Technicians wear special suits and pass through decontamination chambers before touching any component. The white walls and metallic floors reflect the cold light from overhead panels, creating a sense of technological purity. It is here that ordinary materials like aluminum and titanium are transformed into instruments designed to operate for years in space. Much of the assembly is still done by hand. Even with the most advanced machinery, the human touch remains essential for connecting ultra-thin cables, aligning sensors, and adjusting optical components. Each satellite is assigned its own team of engineers responsible for all measurements and testing. The goal is simple: to ensure that the equipment works perfectly from the first to the very last day of its mission. At the end of production, every satellite is placed inside isolation chambers and tested under space-like conditions. Pressure, vacuum, vibration, and extreme heat are all simulated to ensure nothing fails. If everything meets the parameters, the satellite is approved and sent for transport, heading toward the launch base where its true journey begins. Every satellite launched into space has a specific mission. Some monitor the weather and predict hurricanes. Others ensure communication between continents, and some support navigation and defense systems. Even though they are invisible to the naked eye, they are a vital part of daily life for billions of people. When you use GPS, watch satellite TV, or access the internet in remote areas, you are experiencing the silent work of these machines orbiting above us. A satellite's lifespan depends on its purpose and the altitude where it operates. Communication satellites typically remain active for 10 to 15 years, while Earth observation satellites have shorter lifespans due to constant radiation and atmospheric drag. Over time, solar panels lose efficiency, sensors degrade, and the fuel used for orbit corrections begins to run out. Even so, every project is designed to make use of every second of operation. Before the end of its life, technicians on Earth monitor signals and perform correction maneuvers to extend performance as long as possible. When the energy finally runs out, the satellite is deactivated and, in some cases, guided into a controlled re-entry through the atmosphere. Meanwhile, new generations of satellites are already being built. Lighter, more powerful, and equipped with technology that allows them to operate for decades, they show how far American engineering evolves with each cycle. Space may seem distant, but much of what we do here on Earth depends directly on these machines quietly orbiting above our heads. When a satellite completes its mission, silence takes over. It stops responding to commands and begins to drift alone, turning into another metallic fragment in space. Today, thousands of deactivated satellites orbit the Earth, forming an invisible graveyard. They are pieces of antennas, panels, and hulls still spinning at tremendous speeds with no defined path. These fragments represent a growing challenge for space engineering. Even small debris can collide with active satellites and cause irreparable damage. That is why space agencies in the United States and around the world constantly monitor this cloud of objects, tracking their movements and planning avoidance maneuvers. Every fragment is catalogued, analyzed, and followed as if it were still alive. In many cases, older satellites are programmed for controlled re-entry. They plunge back into the atmosphere, where intense friction generates enough heat to turn the metal into fire. From the ground, it looks spectacular, a bright streak crossing the sky as if space itself were returning what it once received. Only the largest pieces survive the complete burn, falling into uninhabited areas of the ocean. Even in their final moments, the process remains calculated, technical, and precise. But space is not infinite. With every new launch, the concern over orbital debris grows. Balancing progress with responsibility is what drives the new generation of engineers to create cleaner and safer solutions for the future of space exploration. When re-entry begins, everything happens in just a few minutes. The deactivated satellite is carefully guided to the point where Earth's gravity starts pulling it back. As it descends, friction with the upper atmosphere produces extreme heat, enough to turn metal into fire. Seen from the ground, it is breathtaking. A glowing trail slicing through the sky, as if the heavens were returning something borrowed. Not all satellites follow a controlled path. Some remain in orbit for decades until they naturally lose altitude and disintegrate. Others, larger and heavier, require constant tracking to ensure they pose no danger. Re-entry is usually planned over isolated regions of the ocean, known as disposal zones, where debris can fall safely. Each return brings a mix of pride and concern. Pride for another successful mission completed, and concern for the environmental impact and the need to keep space clean for future generations. It is the final chapter of a journey that began in an American factory, traveled thousands of miles through the void, and ends quietly above the planet that created it. But while some satellites reach their end, others are already being prepared for launch. New designs, lighter and more efficient, are rolling off the assembly lines. It is a continuous cycle, manufacturing, launch, mission, and return, that keeps alive the engineering that connects Earth to space. Communication between Earth and space is one of the most fascinating parts of this entire process. Each satellite sends and receives data through radio waves that travel in fractions of a second to massive antennas built on American soil. Those antennas decode the signals and transform them into information that reaches us, whether it's a weather forecast, a phone call, or a live image from the other side of the planet. The secret lies in precision. The transmitters aboard the satellite must be perfectly aligned with the receivers on Earth. Any deviation even by a few millimeters can cause a total loss of signal. That is why the factories that build these systems invest heavily in cutting-edge technology and in materials of the highest purity, such as copper and gold, used to ensure flawless signal conduction. Inside control centers, engineers monitor these transmissions 24 hours a day. Through graphs, frequencies, and coded signals, they track the health of every satellite and make real-time adjustments when needed. It is a quiet but vital job that keeps communication alive between space and our planet. And while these signals continue to travel through the air, the next generation of satellites is already being prepared. Faster, more precise, and equipped with more efficient transmission systems, they promise to redefine how the world stays connected, even if most people never realize it. From aluminum forged in American factories to the silent orbit high above Earth, each satellite represents the triumph of human engineering. They carry technology, history, and purpose. They are the eyes that watch the weather, the invisible hands that guide airplanes, and the bridge that links entire continents in seconds. It all begins on the factory floor and ends thousands of miles above us. These discrete machines prove how technology can reshape the world without us even noticing. The GPS that guides a driver, the signal that brings news to your TV, the communication that keeps families connected. All of it depends on those tiny points of light shining in the night sky. Space might seem distant, but in truth, it is part of our everyday lives. And as new satellites are created, the pursuit of perfection continues. Every component, every test, and every launch is a reminder that innovation has no limits. So next time you look up at the sky, remember this. Up there, an entire factory orbits in silence, keeping our planet in motion. Now tell me in the comments, did you imagine that this whole process actually starts in factories right here on Earth? Don't forget to like this video and subscribe to the channel to see more incredible stories about manufacturing, production, and the factories that keep our world moving.